Good morning, students. We will start our class. We find last class. Okay, in last class we had discussed regarding the syllabus. Once we will see the syllabus, once we will go to the syllabus page. Okay, up to now we have discussed regarding the clippers. Okay, we had seen the diode clipper, transistor clipper. In transistor clipper, we have seen the two independent levels. Two independent levels means that is nothing but a empty couple clipper. Okay, empty couple clipper. In diodes also we have seen the two level clippers. Okay, diode also we have seen the two level clippers. For all we have seen the transfer characteristics. Okay, and separately I have mentioned the empty coupled. Okay, that means in clippers we have only two topics, that is diode clippers and transistor clippers. Okay, we have seen all types of diode clippers and all types of transistor clippers. Okay, now we will come to the next topic, that is clamping. Okay, we will see from today class onwards clamping circuits. Okay, very easy. As similar to the clippers, as similar to the clippers, we are going to discussing this campus also. We will find some circuits and we will going to see the how we are going to get the output. Okay, in clampers the difference between the clippers and clampers is here. Here they have mentioned the clamper circuit by using different input. Okay, different input signals. Okay, see the second topic, clamper circuit using diodes with different inputs. That means in previous case in clippers we have seen only for sinusoidal input. Here we have to discuss with different inputs. Okay, therefore we may consider it is a symmetrical waveform. In order to clamp, it may be a symmetrical, it may not be symmetrical. Okay, but we should have the uh, we should have the positive or negative pulses. Okay, we may consider some sinusoidal signals and square waves. Okay, sinusoidal signals and square waves, and we will see the response. Okay, and we will see how the we are going to get the output. Okay, therefore here in clampers only diode clampers. Okay, we will see the only the diode clampers, and we have two more topics, that is the clamping theorem. Okay, we will, the area under the positive cycle and negative cycle should be equal. That we will see the clamping circuit theorem, which is a very important question. Okay, they may ask for 4 marks bit, 4 marks or 7 marks bit. Derive the clamping circuit theorem. Okay, it is some derivation. We will see it. And next practical comes. That means here we may take an ideal diodes. Okay, when you come to the practical, likely that cut down voltages those will be changed. Okay, that we will see in practical clamper circuits and effect of diode characteristics. That means that breakdown all those and transfer characteristics. That means last three topics are can be included in our second topic only. Okay, we will see the clamping operation and diode clampers and clamping circuits. There are only three topics in this chapter. Okay, these transfer characteristics, all these characteristics we will see while discussing along with the inputs only. Okay, fine. Now today class onwards we will start our second part of our first chapter. Okay, these are the clippers, diode clippers. Okay, this is a two-level diode clipper. Okay, and transistor clippers. Similarly, intercoupled transistor, intercoupled a two-level transistor clipper. Okay, now from today class we will start a new topic, that is clamping circuit, clamping circuits. Okay, has similarly to the clippers. Okay, what I have said, clippers means it is nothing but a cutting the some portion of the waveform. Okay, cutting the some portion. That means it may be a positive portion or negative portion. We can cut some portion. Okay, unwanted signal can be removed. Okay, that means while I am explaining the clipping circuits, I have said that if suppose is there any noise signal in our output signal. Okay, noise in our input signal. That means suppose if you consider the digital signal, okay, you only have the ones and zeros. Okay, only you have the ones and zeros. When it is transmitted through some channel, you may get some noise. Okay, we may get some noise here. To clip this noise, okay, to clip this noise, we are going to use the clippers. Okay, when this type of waveform passes through the clipping circuit, and if we are clipped this portion, okay, if we, that means if you cut this portion, the output will be as similar to the your input. Okay, like that we make it. Therefore, for clipping your noise signals, or at the input of the amplifier. At the input of the amplifier should have some limited voltage. Suppose our amplifier works for only 5 volts. If our input having the 10 volts, okay, then we will clip the 5 volts. Okay, that means if the input is having the peak to peak 10 volts, then our amplifier require only peak to peak 5 volts. Then the above 5 volts will going to be clipped out. Okay, therefore the output it will pass through the clipper. Clipper peak to peak we are going to maintaining only 5 volts. We are going to maintaining only 5 volts in the peak to peak. Okay, this is regarding we have seen in the clippers regarding advantages. Okay, now coming to the clampers, what is the advantage? Where we are using these clamper circuits. Okay, mainly these clamper circuit are used as a DC restorer. Okay, that means if suppose if I given the input like this, okay, a sinusoidal signal, this is your DC line. Okay, DC line is at 0. Okay, therefore in this signal there is no DC component. Okay, DC component is 0. Okay, in some of the amplification or some of the electronic devices, they require the DC component. DC component nothing but if you apply a Fourier series for this waveform, okay, Fourier series, here you are going to write as A naught plus AN into I think so you have remember this formula AN into cos theta plus BN into sin theta. Okay, this A naught component is going to representing the DC component. Okay, the A naught component is going to representing the DC component. Okay, in some of the electronic circuits it requires the DC component. Okay, when especially while we are discussing the high pass circuits or low pass circuit in first chapter. Yeah, when it is in square wave input, I have said that if the time constant is very large, if the time constant is very large, the output will be equal to the if we go for high pass circuit. Okay, simply I am recalling your high pass circuit. Actually, you may get this type of waveforms. Okay, this type of waveforms you are going to get. Yeah, as the output. If the time constant is very large, the output may be equal to the input. Okay, we are going to get the output similar to the input, except only difference is the DC component in output is 0. Okay, I had mentioned that point there. Okay, that means whenever a signal passes through a capacitive network, then the DC because capacitor won't allow the DC components. Okay, capacitor offers the high resistance. It may act as an open circuit. Okay, and it won't allow the DC components through it. Okay, for our circuit is starting if we have a capacitor, and after we have our circuit. Okay, the signal which is present here, in this signal if we have any DC components. Okay, you have to assume the Fourier components. Okay, by first seeing the signal you may have a single waveform. It looks like a single sine wave. Okay, but when you are going for analysis, if you apply a Fourier analysis for this waveform, you have an n number of components in this signal. Okay, in this signal we having n number of components. One of the component is the DC component. Okay, when and this capacitor offers the high impedance for the DC, because 1 by 2 pi FC. Okay, where F is 0 means we are going to offering the high impedance. Okay, high impedance for the high impedance for the DC component. Okay, that's fine. When DC this capacitor is offering DC high impedance for DC component will be blocked at the input terminal. Output terminal only we are going to get the AC component. At the output terminal. Okay, therefore the shape will be same. But when you go for analysis, this A naught component will be goes to 0. Okay, for find out for this Fourier analysis, this A naught component will be 0. But some of the applications in our amplifier or in electronic circuits, we require a 227. Okay, it's the final warning for you. If you share your screen or if you write something, you are not allowed into classroom once again. Okay, 227. Okay, then fine. This capacitor won't be allows any DC components. Okay, or if the circuit after this capacitor requires a DC components, then then we are going to place the clamper circuit here. Okay, this clamper circuit will move this waveform to some other ways. Okay, it will move to the waveform to some other ways like this. Okay, once again, today I didn't lock the room. Students keep on entering into the room. Okay, now I will lock the room. If now onwards, if anyone left, join for next class. Okay, today you can't, you are not able to join the class. Okay, if anyone has leave the room, then join for the next class. Today it is not possible. I have locked the room. Okay, this clamper, okay, clamper circuit is used to restore the DC component. That means if you shift the waveform like this, okay, the input signal may be like this, okay, input signal may be like this. If you shift to like this is the new level of your input, okay. The DC component in this signal, the DC component in the signal is this level, okay. Suppose it may be at 5 volts, okay. Therefore, if for this waveform, if you apply a sinusoid Fourier analysis, you may get A naught value equal to 5. Okay. Therefore, the DC level. Okay, we are introducing the DC level in this circuit. Okay. For this waveform, the DC level is 0. Okay, DC level is 0. For this waveform, the DC level which is not 0. Okay, it is having some value. Okay, this is your DC value. Okay, that is nothing but reference. Okay, positive or negative. Okay, therefore for introducing this DC levels, okay, we are using this clamper circuits. Okay, that's why these clamper circuits are going to call as a DC restorer or DC restraint. Okay, that means these are introducing the DC signals, okay, DC components into our input signal. Okay, basically here I have said that when it transmits through a capacitive network, okay, capacitive coupled network, the DC component in the output will be lost since the capacitor blocks the DC. Okay, best example is your high pass circuit. Okay, best example is low pass circuit won't blocks the DC circuit, DC component. Okay, because your low pass circuit like this. Okay, this is capacitor is in parallel. Okay, therefore if a DC component comes here, yeah, it won't allow this direction. It will goes to the output. Okay, therefore rest of the circuit will present the DC component. This is your low pass circuit. Low pass circuit is not going to block the DC component. Okay, when it is an AC high pass circuit, like this, you are going to see the circuit. Okay, therefore, when the signal comes here, it has to pass through the capacitor to enter into the next level. Okay, therefore, this capacitor is going to block the DC component. That's why while we are discussing the high pass circuit. Once if you go through the high pass circuit, there I had mentioned the point also. Okay, especially in the square wave I have mentioned. Okay, if a time constant is very large, these circuits output will be similar to the input except the DC component is 0. Okay, therefore whatever the DC components is goes to 0. If we require for next levels, then we will add a clamper circuit to that. Okay, we will add the clamper circuit. This clamper circuit is going to again restoring your DC component. Okay, restoring your DC components. Okay, here also we have the two types of clamping circuit, which may be a positive clamping circuit and negative clamping circuit. If it is a positive, means complete input waveform shift to the positive. Okay, if we have a biasing, in this also there is a subtopics. Okay, negative clamping circuit with biasing. Okay, positive clamping circuit with biasing voltage. Okay, has similar to a clippers. Okay, if we use some reference voltage, that reference voltage we are going to call as a biasing voltage. Okay, therefore if we use this one, okay, if we use some biasing voltages, then again it will subdivided into negative clamper with biasing voltage, positive clamping with biasing voltage. Okay, like that you can you have subdivided. Okay, you are going to subdivide. Okay, simply a positive clamping means the waveform. If you have a reference voltage, entire portion may not be shifted. Okay, according to the reference voltage. If it is a positive reference or negative reference, if it is a positive reference, it may further shift. Okay, it won't touches the 0. It may goes to the further in upper levels. Okay, if it is a negative clamper, some portion may be present. Okay, some portion may be present in negative side also. Okay, we will see the one by one in each circuit. Simply positive clipper means positive clamper means that waveform, the negative pulse is clamped to the positive side. Okay, this is your 0 level. This is your 0 level. The total waveform, here input side we have a positive or negative pulse. The total waveform is above the 0 level. Above the 0, entire complete waveform is on the positive side. Therefore, this is the positive clipping. Okay, here I have mentioned the DC line also. This is the DC line. Okay, therefore DC line we have introduced the DC component in this waveform. Okay, this is your DC line. Okay, here the DC line is 0. The DC line is at 0 level. Okay, here we have some DC line at Vmax. Okay, at Vmax we have a DC line. Okay, similarly a negative clamper. Negative clamper means the complete waveform. Complete waveform we are going to shifting to the negative side. This is your 0 line. This is your 0 line. Complete waveform we are shifted towards the negative side. Complete waveform we are going to shift to the negative side. Here also the DC line we are shifted from 0 to minus Vmax. This is our DC component. Okay. Uh, Generally, these DC components are we are going to see when we are applying Fourier analysis only. Okay. Otherwise, we may find simply a waveform. Okay. The shape will be same. Okay. Simply it may shift to another level. Okay. This waveform starts from 0. If you make a clamping, it may start from somewhere. Like this, you are going to get output. Okay. It is clamped to next level. Okay. Another level it is clamped. Okay. Therefore, simply depending on the clamping side. If we are clamping to positive side, then we are going to call it as a positive clamper. If we are clamping to the negative side, then we are going to call it as a negative clamper. Okay, and these are further divided into negative clamper with the biasing voltage, positive clamper with biasing voltage. Okay, we will see one by one. This is the introduction regarding your clamper circuit. Okay, basically these clamper circuits, once again this clamper circuit is nothing but defined as, here I write the definition also. The circuit can set the positive or negative peak of the input signal at the required level. Okay, these positive or negative peaks, okay, these positive or negative peaks can be set or can be moved to a required level. Okay, therefore it is nothing but we are going to call it as a clamping circuit. Okay, it is a definition. Okay, simply it will move the positive pulse and negative pulse to a required level. Okay, if you maintain some reference level, this will be clamped to that reference level. If you won't maintain any reference level, it will clamp to the 0 reference level. Okay, therefore positive means entire waveform shift towards the positive side. With here 0 is the reference level. Okay, like that you are going to shift it. Okay, generally these are other names for this clamper circuit are DC restorer and DC reinserter. Okay, why we are calling as DC restorer, DC reinserter means this clamping circuit introduces the DC component in our output waveform. Okay, we require the DC components in amplifier, some rectifier circuits, or some especially in transmitters and receivers. Okay, in communication sectors. Okay, communication sectors we require some DC components waveforms also. If suppose the input signal passes through a capacitor network, automatically the DC component goes to 0. Okay, at the input side there will be a DC component, but when it passes through the capacitor network, it will goes to 0. To again reinsert these DC levels, we will use this clamper circuit. Okay, by using this clamper circuit, we once again inserting the DC levels in our input signal. Okay, therefore here also we have two types of clamping circuits: positive clamping circuit and negative clamping circuits. Okay. Now come to our first one, that is positive clamping circuit. Okay, if we observe clearly, okay, for all the students I am informing, if you understand clearly this positive clamper, no need to explain the remaining concepts. Okay, it's enough. Okay, here I have taken two waveforms. One is square wave and another is sine wave. Okay, for these two inputs, I am going to explain the output. If you understand clearly how we are getting the output waveform, then it's enough. Okay, remaining concepts you can explain. Okay, why? Because I am inserting here. I am not going to explain all the concepts in detail. Okay, similar to a clipper circuit. Okay, in clippers all the concepts I have explained, but here I will explain only with biasing one circuit and a positive clamper and negative clamper. Okay, in exam whatever may be the circuit, you have to draw the output waveforms neatly and you have to explain the output waveform. Okay, therefore all of you listen carefully. Okay, how I am going to explaining this one. Okay, first this is the positive clamper. Okay, the clamper circuit consisting of a capacitor, diode and a resistor. Okay, clipper you won't find the capacitor. In clippers you won't have the capacitor, but clamper circuit we have the capacitor, because to clamp the voltage, okay, to shift the voltage we require this capacitor. Okay, therefore this is your positive clamper. Negative clamper, if you go for negative clamper, this diode gets reverse bias. Okay, this diode anode will be top side and cathode will be bottom side. Okay, I will show the negative clamper also. this is your negative clamper. Okay, so only difference is the resistance may this side or this side, nothing will be happen. Only the difference is this diode. Okay, this diode gets reversed. Okay, anode on top side, cathode on bottom side. That means if you reverse the diode, then the clamping circuit gets reversed. Okay, therefore here I have to consider the positive clamping. As we know that positive clamping means the negative pulse has to move to the clamp to the positive side. Negative pulse has to the clamp to the positive side. Okay, we will see how the circuit is going to work. Okay, here before knowing this circuit operation, here you have to see that one assumption, the time constant. Okay, time constant of the circuit is nothing but R into C. The time constant of the circuit should be very large. Okay, it may be nearly 10 times. Okay, it may be nearly 10 times the time constant of your input pulse. Okay, input pulse. Okay, that means what it means. If I say the time constant is very large, sorry, here I write this small. Uh, time constant RC. Okay, time constant should be very large. Okay, very large. Nearly it may be 10 times the time period of the input signal. Time period of the input signal. Okay, what it means? That means for discharging or charging. Okay, for charging or discharging this capacitor to the full level, it requires 10 pulses. Okay, that means this is the two pulses. Okay, and third pulse, fourth pulse, fifth, sixth, seventh. Okay, it may take the 10 pulses to go to the peak value. Suppose our input peak value is, this is my input signal. The peak value is plus 10 volts. The capacitor has to charge to 10 volts, means it may take 10 cycles, to go to the peak value. Okay, therefore generally for the clamper circuit, okay, for the clamper circuit, we have to choose that the time constant should be very large. Okay, that is a generalized statement. Okay, generally that means in each cycle, okay, once the capacitor charges to full level, next cycle it won't goes to the zero. Okay, that means suppose in positive cycle, if the capacitor charges the full level, okay, a full level means actually negative cycle, again when it reaches to the negative peak, the capacitor has to be discharged to 0 volts. Okay, because it is a plus 10 and it is minus 10. When you are applying minus 10 volts, the capacitor has to be discharged if it is a time constant is low. Okay, that means the capacitor will slowly charges to 10 volts, and slowly it will discharges to the 0 volts. Okay, it take more time. Okay, in between this charging, it may complete our input pulse as then 10 pulses. Okay, it may take around 10 pulses to go to the peak level. Therefore, this point you have to keep in mind before starting our discussion. All the clamper circuits, what are the clamper circuit? For those clamper circuits, the time constant is very large. Then only you will get the clamping waveforms. Okay, therefore you should not take the time constant is very less. Okay, now we will see the first sinusoidal signal. Okay, when you apply a sinusoidal signal to a positive clamper. Okay, if we apply sinusoidal signal in positive cycle, what happens? This diode is in reverse bias. Okay, because this is connected to the positive. Okay, this is cathode is connected to positive, anode is connected to the negative. Therefore, it is in reverse bias. Therefore, this is open switch, and the input voltage. Okay, as the input voltage rises, since the time constant is very large. Okay, it won't goes to the peak level. Okay, whatever the input, it will be allows to the output terminal. Okay, therefore our output may be, this is our output waveform. Output will be as similar to our input signal. Okay, in positive cycle, your output may be equal to the input signal. Okay, while coming to the negative pulse, when you come to the negative pulse, this is at minus and this is a positive. Therefore, diode is in forward bias. Okay, if diode is in forward bias, means diode gets short circuited. Okay, once the diode is short circuited, okay, what happens? There is no use of this resistor. Okay, there is no use of the, because parallel it is short circuited, entire current flows through this branch only. Okay, there is no current in this branch. Therefore, I am taking this as an ideal diode. Okay, therefore forward resistance is 0. Okay, the resistance value is 0 in this branch. Therefore, we can remove this resistance. Now the time constant of the circuit is R into C. C value we have, R value is 0. Therefore, time constant is nothing but when diode is on, time constant is 0. Therefore, immediately the capacitor charges to the peak value. Okay, when diode is on, the resistance in our circuit. Okay, the resistance in our circuit is 0 because I had taken ideal forward resistance. Forward resistance for this diode is 0. Okay, and parallelly it is short circuited. Therefore, this branch won't comes into picture. Okay, therefore our circuit is nothing but only capacitor connected to the input signal, that is minus pulse. Okay, therefore if it is if it is a negative cycle, means this terminal will be minus and it will be positive. Therefore, our capacitor will charge in this direction. Okay, our capacitor will charge in this direction. Therefore, here we may have the positive terminal and this is negative terminal, and capacitor will charges to the VM. The capacitor will charges to the VM volts. Okay, suppose our input is 10 volts, therefore capacitor will charges to the 10 volts. Okay, I have taken my input voltage as 10 volts. Therefore, in this direction, it charges to the 10 volts. That means this is the positive terminal, this is the negative terminal, and it charges to the 10 volts when diode is in on condition. When diode is on condition, that means as the voltage reaches to minus 10, when the input signal, okay, you observe the input signal, when the input signal reaches to the this minus 10 volts, capacitor reaches to the 10 volts. Capacitor will also charges to the 10 volts because the resistance value is 0. If you have a resistance, then the time constant is very large, R into C. Okay, therefore it will take more time. In previous positive cycle, the diode is in reverse bias. We have the resistance in our circuit. Therefore, time constant is R into C. Therefore, it won't charges to the peak level. Okay, because time constant is very large. Okay, it may charges to the 1 volt or 2 volts. Okay, it won't goes to the peak value. Okay, but in reverse bias, in negative cycle, diode is in forward bias. Therefore, diode will be on and the capacitor charges to the peak value because the resistance value is 0 in our circuit now. Okay, therefore it will charges to the 10 volts, and this is the positive polarity and this is the negative polarity. And what about the voltage, output voltage? Okay, since it is a short circuited, okay, output terminal is short circuit, across the output we have a short circuit. Therefore, we are going to maintaining the 0 volts. Therefore, up to this level, up to the minus VM, okay, up to the half of your negative cycle, our output will be maintained 0. Our output voltage will be maintained 0. Input will be as similar to your first cycle, input will be as similar to your, and up to the minus VM. Yeah, that means half of your negative cycle up to this point. Okay, this is I represented here. Why we are getting this 0 means this 0 is nothing but a due to the short circuit, okay. Now if we at this point, okay, at this point, if we observe the our input voltage is at minus VM, that means minus 10. Okay, minus 10, and then after our input voltage is increasing, okay, that means it may goes to the minus 9, okay, minus 8, and then to the 0. Okay, that means in this portion we observe this is at minus. Okay, this terminal is positive. Positive is connected to your cathode. Positive terminal is connected to your cathode, and this one is also connected to a positive terminal of your supply. If you observe the resultant voltage, this is at plus 10. This is at plus 10, and this is at minus 10, minus 9. Okay, because our voltage is increasing. Okay, our voltage is increasing. Therefore, it may be a minus 9. Okay, minus 9, minus 8. Like that, the voltage is increasing. And therefore, if we take the input voltage V in plus Vc, okay, this is the voltage across the output. Okay, V in is at minus 9, this is at minus minus 10. Okay, minus 10. Therefore, you may get the minus. This is a plus 10. Capacitor plus positive terminal is connected at the output terminal. Therefore, this is at plus 10, and it is connected to a minus 9 volts. Input voltage is minus 9 volts. Therefore, resonant voltage is plus 1. Resonant voltage is plus 1. Okay, plus 1 will be occur here. Therefore, capacitor gets off. Okay, capacitor gets, because cathode side we are getting the positive voltage. Cathode side we are getting this is a plus 10 volts is connected here, and plus 9 volts is connected here. Anode side. Okay, I think so you are following my class. Input voltage is minus and plus, like this. Okay, this is minus. We are still in negative cycle only. Okay, minus and plus. Therefore, this voltage is 9 volts. Therefore, anode is at 9 volts. Cathode is also plus terminal is connected. Therefore, cathode is at plus 10. Okay, therefore cathode is having the more voltage when compared with the anode. Therefore, diode will be off. Okay, that means at this point, okay, when the input voltage reaches to the minus Vm, our diode becomes off. Why? Because means the anode getting the more voltage when compared with the cathode. Okay, whatever the voltage, minus 9, minus 8, whatever may be, it may be 9, 8, 10. Okay, anode side voltage is decreasing, cathode side voltage is maintained constant. Okay, because this diode is off state, this resistance comes into picture and time constant is very low. The capacitor won't discharge quickly. Okay, therefore it may act as an voltage source. Okay, battery capacitor may act as a battery and it is maintaining the 10 volts constant for after a large time period. Okay, after large time period it may goes to zero. Okay, therefore at the immediately in this period, okay, the capacitor is going to maintain a constant voltage. Therefore this diode will be off. Okay, when this diode is off, what about the output voltage? Okay, that is resonant voltage. Okay, this will be minus 9 and this is 10. Therefore output is 1 volt. Okay, and as it goes to the 0, my input signal goes to 0 means 0 plus 10, output voltage is 10 volts. That means from here onwards output voltage may rises linearly. That means when the input voltage reaches to 0, when the input voltage reaches from minus Vm to 0, okay, in this period only, okay, I am saying half of the next portion. Okay, input voltage reaches from minus Vm to 0, our output voltage reaches from 0 to Vm, 0 to Vm. Okay, because our output voltage is nothing but a V in plus Vc. V in plus Vc. Okay, Vc is 10 volts. Plus is connected. Plus is connected. Therefore, this will be 10 volts. Okay, our input voltage is at minus levels, minus 9, minus 8. Okay, therefore, when we add these two voltages, we may get a positive voltage. That positive voltage will be finally when it is at 0. When our input voltage reaches to 0, output voltage will be at 10 level. Okay, therefore, this is my 10 volts. Okay, therefore, it may comes to this level. Okay, when the input voltage again rises, okay, in positive cycle this diode will be again in off position only. Therefore, when input voltage rises from 0 to 10 volts, okay, our output, these two will be added. Okay, therefore this may be in positive and this is negative. These two will be gets in series. Therefore, output voltage reaches to the 20 volts. Output voltage reaches to the 20 volts. This is your output voltage. Okay, this is your output voltage. Okay, output voltage will be at 20. Okay, again when it is input voltage is decreasing, input voltage is decreasing means when it reaches to 0, capacitor is maintaining constant voltage because time constant is very large. Therefore this voltage will be again decreases and comes to 0, comes to 10 volts. Okay, because there is a 10 volts fall in the input, therefore it may comes to the 10 volts. When it is at minus 10, okay, when again it goes to the negative cycle. Okay, when it is minus 10, our input, our output may goes to the 0. Okay, because the input side here we have minus 10, capacitor is having plus 10, both will be gets 0. Therefore our output may be goes to the 0, and again from minus 10 it may rises to 0, again from 0 to it goes to the 10 volts, it may goes to the 10 volts. Okay, and in positive cycle again. Okay, therefore the cycle gets repeated. Okay, and it will be continued. Okay, if we assume that all these cases we had assumed that our capacitor is maintaining 10 volts constant. Why we are consider that it is maintaining a 10 volts means if we take the time constant is very large, the capacitor won't get discharged quickly. Okay, therefore once it charges to the 10 volts, it will maintain a 10 volts for a large period. After suppose after 1 second or 2 seconds, when this voltage reaches to 0, capacitor voltage reaches to 0 means again it may start from here. Okay, therefore again it may comes to 0 and again it may first cycle will be as it is and again it may start. Okay, like that it may continue. Okay, once the capacitor is maintained with constant voltage, we are going to getting the constant pulses. Okay, the which may having the peak to peak, that is 20 volts. Okay, peak value is 20. Our input is peak to peak is 10. Okay, 10 to 10. Okay, here 0 to 20. Entire negative pulse is shifted to the positive side. Entire negative pulse is shifted to the positive side. Okay, all this explanation will be true only if the time constant is very large. Okay, that's why I have mentioned starting only the time constant should be very large. Okay, once the time constant is very large, then only we will get this type of waveforms at the output terminal. Okay, this is regarding when you apply a sinusoidal signal. Okay, and this portion, up to this portion we may consider as a transient. Okay, Therefore, when you are drawing the output for a clipper, suppose this is my input signal, okay, some peak to peak, okay, peak to peak you may have the 10 volts, and this may be a minus 10 volts. Then your output voltage, if you want to draw the output voltage, it may start from 10, okay, like that you are going to draw, okay. Exact at peak, okay, minus Vm, it may goes to 0, okay. Exact at plus Vm, it reaches to the 20 volts. This will be at 20, okay, like that. This portion is nothing but a transient portion, okay. Previously we are not getting the 20 volts, okay. Therefore, up to this, from here onwards we are going discussing our output, okay. This is my output, okay. This is my output waveform, okay. But before we are having some waveform, okay. For understanding, I have mentioned this waveform also, okay. This is nothing but they will consider as a transient, okay. Therefore, starting they may cut this portion and simply they may give this type of waveform, okay. That means if suppose this is your input waveform having some sinusoidal signal which may start from 0, and your output may be start from somewhere, okay. This like waveform you are going to get. It is starts from Vm. Okay, our output will be starts from Vm and reaches to the peak level. Okay, reaches to peak. Okay, they won't draw this waveform. Okay, they won't draw this waveform. Okay, but if you from the 0 onwards, at the time period 0 onwards, if you discuss, you will get this waveform also in the output table. Okay. This portion they are going to consider as a transient portion, and this portion is the steady state output. Okay, steady state output. Once the capacitor charges to 10 volts, and then after we are getting this portion, therefore this may be called as a steady state. Steady state we are going to getting a peak 20, okay, 20 to 0. Okay, peak to peak we are going to having the 20 volts. Okay, here also peak to peak. If we observe peak to peak, here also it is the 20 volts. Okay, plus 10 and minus 10. Plus 10 volts, minus of minus, we may get plus. Okay, therefore here also peak to peak. If you observe the peak to peak voltage, it is at 20. Here also, if we observe the peak to peak, it is at 20 volts. That means in clamper circuits, the peak to peak voltage can't be changed. Okay, peak to peak value will be maintained constant. Okay, the peak to peak value will be maintained constant. Only it will be shifted. Okay, only it will shift to the negative portion to the positive portion. Okay, therefore this is your actual output. Okay, when you neglect the transient analysis, transient portion, like this you are going to get the output. So like this you are going to get the output. Okay, this previous portion no need to draw. If you draw also nothing is wrong. Okay, this is your transient portion. Okay, now same circuit we will observe for the square wave. We observe for the, if we apply a square wave has an input. Okay, if we apply a square wave as the input, what will be the output we will see. Okay, here also I will start from 0. Okay, I will start from 0 onwards. Okay, here the input voltage is plus V. Okay, at 0 instant, if suppose this is 0 instant, your input voltage is at plus V volts. Okay, in plus V, if you apply the plus V, diode will be in reverse bias. Diode will be in reverse bias. Once the diode is in reverse bias, we may get the output. Here I didn't draw the transient portion. Okay, directly I had drawn the steady state portion. Okay, that's why I will draw here. Okay, how you are going to get. Okay, when we are going to observe at the positive, at the time instant 0, at the time instant 0, we are going to applying the plus V. Okay, and when it is in plus V, diode will be in off state. Okay, once diode is off, we may get the output. Okay, output is plus V. Okay, output will be because diode is off, whatever the input that will be transferred to the output. In this portion, capacitor won't charges to the peak value because there is a resistance. Time constant is very large. Okay, capacitor may charges to some portion. Okay, it may not goes to the peak value. Okay, and when you are applying the negative pulse, diode gets forward bias. Okay, because this is a minus. Suppose it may be a minus 10 to plus 10. Okay, peak to peak. Okay, minus 10 to plus 10. When you apply the minus 10 volts. Okay, at this some time interval. Okay, at this time interval, the input voltage is minus 10. When you apply the minus 10 here, this diode gets forward bias and diode gets short circuited. When the diode is short circuited, this resistance is also short circuited. Okay, parallelly both will have the short circuited. Therefore, now the circuit resistance is 0. So if I take this as an ideal diode, if I take as ideal diode, circuit resistance is 0. Once the circuit resistance is 0 means capacitor charges to peak value. Okay, my peak voltage is 10 volts. My peak voltage is 10 volts. Therefore, in which direction it is going to charge? Okay, this is the negative direction. Therefore, this will be minus and this will be a positive. Therefore, capacitor charges in this direction. Okay, negative pulse. Okay, positive pulse means it may be a positive or it may be a negative. Okay, we are in negative cycle, therefore minus and plus. Okay, capacitor charges plus and minus. Okay, therefore when it is on, when the transistor, when the diode is on, output voltage will be maintained 0. Output voltage will be maintained 0. Okay, and capacitor charges to the 10 volts. Okay, for a sinusoidal up to half we have considered. Okay, but in square wave, okay, completely, okay, there is no time varying pulse here. Okay, therefore complete this period, diode will be on and the output voltage will be maintained at 0 level. Okay, output voltage is maintained at 0 level. Okay, and again in second positive pulse. Okay, when it is in second positive pulse, and again diode gets forward by reverse bias because it is a positive cycle. Therefore, diode will be in forward bias, and we we will have this resistance. Okay, we will have the resistance in our circuit. Okay, therefore now the diode, okay, plus 10 volts. Okay, this is plus 10 volts. We are at positive terminal. Okay, we are applying positive. Therefore, our output voltage will be like this. Okay, plus and minus. Okay, because we are positive. Therefore, here also plus is connected to minus. Okay, and minus is connected to the output. Therefore, these both are in series. Both are in series. Okay, therefore plus 10 and plus 10. Okay, totally 20 volts. Therefore, our output may goes to the plus 20 volts. Output goes to the plus 20 volts. Okay, output will be when in this portion. In this portion, our output will be 20 volts. Okay, our input is at 10. Okay, output will be at 20 volts. Okay, when it is 20 volts, and when the input signal goes to the minus 10. Okay, minus 10. Okay, when it is at minus 10 means here it will be at minus 10 volts. Okay, here it will be, because it is not a sinusoidal, it is a square wave. Voltage will be maintained constant. Okay, therefore this is minus 10, anode is at minus 10 and cathode is at plus 10. If we assume the time constant very large in previous cycle, if the capacitor won't discharges, it will be at plus 10. Okay, that means both are in equal potential. In previously, okay, in previous cycle, okay, it may discharge by 0.1 volts. I think if we are consider the time constant very large, then also there is a small discharge. It won't discharge completely. If it discharges by 0.1, capacitor discharges by 0.1, your cathode voltage will be at 9.1. Okay, it may not be at 10, because in previous cycle when you are maintaining at 20 volts, at that time both are going to delivering the current to this load. Therefore, this is 10 volts, and the capacitor may slightly discharge. Slightly it may discharge. Okay, it may discharge by 0.1 volts also. It may having the 9.91. Okay, 9.91 means again diode will be on, because the anode having the less voltage, 9.9. Simply I had assumed that only 0.1 drop. Okay, because time constant is very large. Okay, therefore if a small drop will be occurring in this capacitor, then also this diode becomes forward because cathode is at less potential. This is connected to the capacitor. Okay, capacitor voltage is at now 9.9 volts. Okay, our input voltage is at 10 volts. Okay, therefore diode will be forward bias. Again it will be short circuited. In negative pulse it will be short circuited. Therefore our output voltage goes to 0 once again. Okay, negative cycle it may goes to 0 once again. Okay, when you get the positive cycle, again this both will be added. And again we may get in negative cycle diode is off. Therefore this 0.1 volts will be charged by this capacitor. Okay, again capacitor voltage is 10 volts. Therefore total voltage will be maintained at 20 volts. Okay, again in negative cycle it may goes to 0. Like this it may continue. Okay, this is our transient portion. Okay, this is our transient portion, and from here onwards we may have the steady portion. Therefore this is the practical. If we consider the practical, there will have some 0.7 volts drop. That I have represented in the negative portion. This is the practical. If you consider the practical, you may get like this. Okay, this is your breakdown voltage 0.7. Okay, if we take it as an ideal, okay, simply it may start from 0. Okay, no need to represent this practical one. Okay, simply it may start from the 0. Therefore, the output voltage will be from 0 to 20 volts. 0 to 20 volts. This is the steady state. Okay, I had removed this portion. I had removed the transition portion, and I had taken only the steady state waveform. Okay, therefore this is our steady state waveform. From 0 to 20 it is going to vary. Okay, 0 to 20 it is going to vary. Okay, I think so you have understand the this one. Okay, clipper, positive clipper for a sinusoidal signal and for a square signal. Okay, in sinusoidal signal the diode, once it is in off position, it will be off for a long period. Okay, it was, but in square wave it will be on and off. Okay, for positive cycle it will be off, or negative cycle it will be on. Okay, because this diode, this capacitor may charge discharge at least 1%. Okay, when it is delivering the power to this load in positive cycle, the supply voltage and this one both, here also it is going to discharge. Okay, here also it will discharge, but here in sinusoidal we are not considering the discharge. Okay, but here the diode gets be on. Okay, diode will be on. Okay, if it is this portion, okay, when it reaches to 0, at this time interval the capacitor may charges back. Okay, if it is a sinusoidal, when the input signal reaches to 0, at this time it may charges. Okay, it may charges, and it may maintain the constant voltage. Okay, when it is short circuited the time constant is 0, therefore quickly it is going to charge. Okay, when it is off, we are maintaining a large time constant, r into c. R into c is having the large time constant, therefore it will slowly discharges. Okay, this is regarding your positive clipper. Okay, for a square wave and sinusoidal. Okay, if you have any doubts, okay, if you have doubts you can ask. Okay, otherwise we will go for the negative. Okay, negative clamping. Okay, we will see the negative clamping in next class. Okay, for today, if we have any doubts,